any questions at any point, please feel free to raise a hand or shout something out, and we can dive a little deeper on that, because this is not a simple topic, and you know, there might be some questions. So let me pull up my slides here. Yeah, so today I'm going to be talking to everybody about optimizing Rust code. So a little bit of background about myself. I've been doing Rust since before the 1.0 release of the language, which at this point was a little over 6 years ago. I honestly don't remember why I got into the language. I think I was kind of a language nerd in college, just picking up anything that seemed interesting or weird. And Rust definitely fit that bill. And been using it for side projects for several years, and then I've been using it professionally in an engineering role at OneSignal for the last 2 years. And then also for the last year, I've been writing the book Refactoring to Rust, which is about replacing performance or safety critical pieces of code written in other languages in order to make your existing software programs faster or safer without totally rewriting them. So before we get started on our optimizing content today, I need to give a significant disclaimer. So if you have not seen my RustConf 2021 talk, optimizing Rust code is not something that you should do just because you can. It's not Everest. It's not like, I guess you can do it as sort of an academic exercise, and it is fun, it is rewarding. However, you often wind up with code that is trickier to understand, trickier for new people certainly to read and understand. And nothing that I'm going to be talking about in this presentation is necessarily a best practice. So if somebody hands you a problem and tells you, hey, please solve this problem for me in Rust, you should probably not start by reaching for these tools. You know, you should always start by trying to solve the problem first. And then once you observe that your system has some performance issues that you want to improve, then you can start reaching for these things. But if you can't solve a problem slowly, you probably can't solve it quickly, unless there's some, you know, inherent timing restriction on your problem. Also, none of the tips that I'm giving in here are intended for beginning Rust developers, so if you're not doing all these kind of crazy performance optimizations, you should definitely not feel like, oh, I'm a failed Rust developer, I'm not achieving the full theoretical performance benefits of the language. No, that's not what I'm trying to tell you at all. So these are things that you can do when you believe that performance is a bottleneck. These are not things that you should do from the get-go. All right, now that that's out of the way, let me tell you a little story about something that came up at work for me about a month ago and inspired this talk. So I work as an engineering manager at OneSignal on the infrastructure services team, and our team is responsible for maintaining internal services like gRPC services, Kafka consumers, Redis servers, Postgres servers, all kinds of things. Relatively small engineering team, so we have a lot of services that we manage. And one day we started getting paged because a Redis server was getting sort of close to its memory limits. And we were able to extract a text file containing about 3 gigabytes of new line delimited data on every single key that was on this Redis server. And I wanted a way to figure out what are the patterns of the keys that are in this file, how frequent are these various patterns, and therefore, like, you know, is there some super high unexpected data cardinality in there? Like, are we dumping a bunch of things that have like OneSignal : user : something into the Redis database? And if so, like, can we look at the user generation code and figure out where the problem is? So I had a 3 gigabyte text file. I need to find patterns in it. And I recalled that we use Datadog as a log aggregation service, a SaaS tool, and they have basically just a tab in their UI that does exactly this thing. It, you know, you upload your logs to Datadog, and one of the things you can do with those logs is have it automatically detect patterns and their frequencies for you. So I knew that this is something that could be done because Datadog and other SaaS log providers did it and they made it really easy. But I didn't necessarily want to use a SaaS log provider to solve this problem because I didn't really want to wait or pay for uploading 3 gigabytes of data to the cloud. I didn't really know if I could test this on a smaller scale with a cloud provider, and it didn't really seem like Datadog had options for configuring the clustering settings. So like if I wanted to, sort of tune the delimiters or tune the tightness on the pattern recognition, it didn't really seem like that was an option. So I really wanted to find a way to do this locally as opposed to in the cloud. So I searched for log pattern analysis CLI, and I discovered this tool, LogMine, which, as the slugs tell us, is a log pattern analyzer CLI. And it is based on a research paper done by some folks at the University of New Mexico and NEC Labs, also called LogMine, which is an algorithm for doing unsupervised pattern analysis specifically in log files. So I downloaded the tool, I pointed it at my, actually I didn't point it at the raw file, I pointed it at a test file that I had generated that was pretty large, and I checked the throughput on it. And I was not really impressed initially. So you can see here I'm piping the data through PV, and the LogMine tool is chugging at around 500 kilobytes per second, which is not super fast, especially considering I needed to process 3 gigabytes of data. So this would have taken several hours to process, and if I determined that, after the analysis was complete, I needed to change some settings, do something differently, that would be another several hours that I would need to wait for the tool to run again. So this wasn't really acceptable performance for me. So I went back to the tools page, and I saw that it was written in Python. And this led me to the conclusion that I could probably make something that was faster, significantly faster, in Rust. And so I set out with a goal: re-implement the core of the LogMine tool with as much performance as possible. So this tool had a lot of different options that I didn't necessarily care about. I really just wanted to be able to do the basic pattern analysis, and I wanted to do it as fast as possible. So this led me to create LogMine RS, which is a Rust rewrite of LogMine with an explicit goal of being as fast as possible. And spoiler alert, the Rust version is a lot faster than the Python version. So you can see here, the Rust version is running at 136 megabytes per second, which is nearly 275 times faster than the Python version. And this did not happen straight out of the gate. This was like an iterative process where intermediate changes built on each other, and it got slowly more performant over time. And those, where's my graph? It's not showing up. It's not showing up on that slide either. Okay, well, I had a very beautiful graph showing incremental performance steps, but suffice to say, the naive Rust version was still about 10 times faster than the Python code. So still a very significant performance difference just from that initial naive rewrite that had none of these optimizations applied to it. So that was essentially the thesis of my RustConf talk, that, you can get very good performance just from a naive Rust rewrite of tools in dynamic languages. There's not always a need to do these kind of severe optimizations, but I treated it as kind of an academic exercise, and that's why I did them all. So how did we get here? How did I get from 10 times faster to almost 300 times faster? There are many steps that I took, but the number one most important thing that you can do for performance is measure it. If you cannot measure the performance of your software, how could you possibly hope to improve it? And consequently, how can you possibly hope to ensure that performance does not get worse when you are making changes unrelated to performance? When you're adding a new feature that you think is not going to have a negative performance impact, if you don't have a way to test that and assert that the performance didn't get worse, you don't know. So measuring is a super important step you can take. So different things that you can use in the Rust ecosystem in sort of decreasing order of goodness. Criterion.rs is a benchmarking harness that you can use from stable Rust. Some of you may know that the nightly channel in Rust has a benchmarking tool that you can opt into as a feature. But if you're on the stable version of Rust, you can use Criterion, and it's actually a fantastic benchmarking tool with really great statistical analysis. I will be showing some output from Criterion later on in this presentation, but that's a very strong recommend. Failing that, if you can't use Criterion, it doesn't always work. Excuse me. Indicatif is a progress bar crate that you can pretty easily add to your Rust tools to check on how things are working. One of its really easy functionality is you can just wrap a IO object, and then it will automatically give you performance numbers for that IO object. Failing that, GNU PV is something that I used in a previous example, where it will just show you the performance of data going over a command line pipe. And so if your tool takes input from standard input, then PV will show you, bytes per second and progress and ETA on your tool. Failing that, if you don't take standard input, you can just use wall time. It's not a great tool, but it does work, and it is certainly better than not having any way to measure the performance of your system. But yeah, measurement is super important. As we'll see later on, some of these things that I did I thought would make performance better, and they actually made them worse. And the only way I knew that is by having a measurement in place. Here's a broad summary. We're going to go into much more specific detail on all of these points. But broadly speaking, I used Parallelism to leverage all of the cores that were available on my computer, and I also tried to reuse memory as much as possible in order to increase single core performance. Yeah, so let's first jump into the strategies that we could use for memory reuse. So broadly speaking, again, allocations are expensive. It is not free to ask the OS to set aside more memory for you, and it's also not free to ask the OS to deallocate memory for you. And especially in Rust, where we have drop, it can sometimes be expensive to deallocate types because you might run an expensive drop handler. So Rust makes it relatively easy to avoid these allocations. There are lots of instance methods available to us on Vec and string, which is, for those who don't know, string is basically just a thin wrapper around Vec. And these methods allow pretty easy memory reuse. So let's jump into some of those. The first one is clear. So clear allows you to basically delete all of the items that are inside a vector without deallocating the underlying storage, the underlying allocation in memory. So if you're repeatedly filling up a buffer using the data in it, then throwing the buffer away, you can use clear instead of vecnew to get an empty buffer instead of using vecnew to get a brand new buffer. So you can see here, in this top example, we're creating a new vector, we're filling it with new data. In the bottom example, we are reusing an old vector and we're calling clear on it and we're filling it up with new data. So down here at the bottom, there is output from Criterion that shows we get about a 40% speed up on filling a 400 byte buffer by using veclear instead of allocating a fresh buffer with vecnew every time. Oh, have there been any questions anybody has about anything that I've said so far? Super. Vectrain is sort of similar to clear in that it allows you to remove elements from a vector without changing its underlying storage. The difference is this actually iterates over the elements that were in the vector and gives them back to you as owned values. So if you were using vec into iter, as we do in this top example, to iterate over a vector by value, you can replace this with Vectrain to still iterate by value, but retain the underlying buffer space and reuse an allocation. So similarly to clear, this would allow you to save on allocations and would help you to improve performance if you're repeatedly using the same buffer over and over and over again. Next, this is kind of a strange one for folks to wrap their head around. Cow is a fairly simple enum that's in the standard library that allows you to use either owned or borrowed values from the same type. So it allows you to avoid allocations until it's absolutely necessary to do them. It can be used in both parameters and return types, but let's take a look at this example on the right where it's used as a return type. So we can see in this top example, we have this do something function. It takes a stir slice and it takes an integer and it returns an own string. And if the number that's input is even, we add a divisible by 2 suffix to the string and we return it. And if the number is not divisible by 2, we just return the initial data as a pass-through. So this function has to allocate on both branches. You see the bottom branch has to create a string, an owned string, even though there are no changes that are being made to that string. So it's not strictly necessary from a logic perspective that this needs to allocate, but it is necessary from a type perspective because, of course, the function is returning an owned string, so both branches have to return an owned string. It's not possible for this function to return a string slice because the top branch actually does need to allocate, and you can't return a borrow of something that's allocated within the function that's returning the thing. That's sort of a constraint on the way lifetimes work. So what we can do instead is we can return a cow. We can see in this bottom example, we've had to add a lifetime annotation, lifetime A, and we've added that annotation to the borrow on our string slice, and it's also the lifetime parameter of the cow that we're returning. So the real cow type is slightly more complicated than the one that's in the bottom left of this slide, and that's basically to allow the coercion between things like str and owned strings in the owned and borrowed variants of the cow. But suffice to say, in the real cow, the owned variant for the stir type is a heap allocated string. So we can see on these two branches now, the top branch does do its allocation and it returns an owned cow. The bottom branch does not do any allocation and it returns a borrowed string slice. So this could also be useful in a parameter type as well as the return type as it is here. If old data was passed through as a cow, then we would be able to so the problem with the function as it exists right now is if somebody already had an owned string sitting around and they wanted to call this function, they would have to take a borrow on that owned string to pass it to do something as the old data, and then if I was divisible by 2, they would then do a reallocation inside this function. But if we passed in a cow to do something, then we would be able to not reallocate again because it would be able to tell that, oh, there's already an allocation. This old data is already allocated on the heap. We can do the mutation without having to do another allocation. Questions on that one? Because this is a weird one sometimes for folks to wrap their head around. Okay, great. Std_mem_take. This is a little bit simpler to wrap your head around. This is sort of similar to a swap function, but it always swaps with the default value of a type. So in this example, we have a processor struct that has some Swapspace on it, which is just an i32 vec. And that Swapspace is used to do some intermediate calculations every time this do something function is called on the processor. So the first thing we do is we pull the Swapspace off of the processor by using std_mem_take. So this takes the owned the owned vec of i32s out of the swap space, replaces it with an empty vec, which is the default value of vec. And an empty vec, an empty string, these actually require 0 heap allocations. So you can create as many of these as you want without having to do any heap allocations, very cheap to create. So we do this, we get the swap space off of the processor, we clear the old data out, we call a function that requires an owned vec and returns a new owned vec, and then we repopulate the swap space with the thing that came back from that computation function. So again, this just allows us to defer an allocation by having some recurring swap space sitting out there. And it allows you to move data out of a reference. So this is actually one of the things, and this is somewhat of a tangent, but this is one of the things that if you're familiar with the async APIs at all and the pin system in Rust, this is one of the functions that the pin system blocks you out from using because it allows you to move things out of a reference. Stdmem transmute. So transmute is probably one of the most easily misused functions in the standard library. If you don't count deprecated functions, it is probably the most easily misused function in the standard library. Extremely dangerous if you don't know what you're doing. There are a lot of invariants that you have to uphold yourself. And it basically says to the compiler, hey compiler, I know that you're working really hard to keep track of all these types, and you're really sure that this thing is an X. But I'm a developer and I'm really smart, and it's actually a Y. Just trust me. So it actually contains no runtime code whatsoever. It's just a compiler built in that changes the compiler's, it basically just changes the type of a value. So it takes in an owned value of one type, it returns to you an owned value of the other type just by reinterpreting the raw bytes. Extremely dangerous. I think the one safety thing that they were able to add to it is if the types do not have the same size at compile time, then the function will not compile. But it is useful in very limited circumstances, and it is safe to use in various limited circumstances. One of these, as this function on the right shows, is changing lifetimes on a empty vector. So one of the very easy ways to misuse transmute in a way that makes your code blow up at runtime is by changing the lifetime on a reference value. So frequently when folks coming from a language like C++ discover the transmute function around the same time that they have discovered lifetimes, they will try to do something like transmute a string to the static lifetime. And that is extremely problematic and does not work. Well, I mean, it compiles, but it does not work. And the reason why this function here on the right is safe is because of this clear right here at the top of this function. So there are actually no values that exist. There are no like reference values that actually exist at the time that we're calling transmute to be invalidated. So the vector is totally clear. The absolute only thing that is changing here is a compile time value, the lifetime value of values that do not exist yet. So this is safe, but generally speaking, transmute is extremely problematic, and you should be wary when you see it. The actual real code in my logmine tool that has transmute in it has a lot of comments explaining why it is safe, why it's okay, and you should be very wary when you see transmute in the wild. Yes, but it is, in very limited circumstances, useful. And the utility of this function may not be immediately apparent to you, but it was necessary for me in my circumstances to avoid an allocation that I needed to be able to swap out a cow of borrowed strings for a cow of static strings, or sorry, a vec of cows of borrowed string to a vec of cow of static string, because I needed some. Actually, it was similar to this example. I actually had a swap space of vecs sitting around, and I didn't want to put a lifetime annotation on the processor that I was using, so I wanted that swap space to be a vec of cow of static strings, so that I didn't have to put a lifetime annotation on the processor. But then when I was actually using that swap space in practice, it needed to be able to hold borrowed strings on it. So this function allowed me to switch between those two things at will. Questions on transmute, because again, very tricky subject that some people have questions on. Yes.
Sorry, I'm getting through. Not directly to transmute, but you said there are other now deprecated functions that are also very, very dangerous. Can you sort of elaborate on that for a bit?
Yeah, that is a great question. And let me pull up the docs for that, because the docs for this function actually tell you, hey, please do not use this function because it's basically impossible to use correctly. And
mem uninitialized.
Mem uninitialized, correct, yes. So mem uninitialized, as we can see in the docs here, it says the reason for deprecation is that the function basically cannot be used correctly. So mem uninitialized hands you an owned uninitialized value of type T. However, like this, if you're coming from C or C++, like this sounds totally fine, totally pedestrian, because that's how the language does every single value. However, the Rust compiler, one of its invariants is an owned value of type T will always be initialized and always hold valid data. So this function basically breaks that assumption of the compiler that there will always be a valid value of type T in every single variable. So this function basically cannot be used correctly, as the docs allude to here. So it was deprecated in Rust 139, and it was replaced with the maybe uninit type, which allows you to create uninitialized memory that the compiler does not, that the compiler knows is uninitialized. So it allows you to differentiate between uninitialized and uninitialized and initialized memory, whereas this function, it has no differentiation between memory that was created from this uninitialized function and values that were correctly created from, constructors or whatever. Great question.
Great, thanks.
Yep. Anything else before we move on?
So if any benchmarks for the cow.
Sorry, I couldn't quite hear. Could somebody repeat the question?
I was wondering if a couple of slides ago when you were showing use of cow, I was wondering if you had any benchmarks showing the performance increases of using that over using string allocation.
That's a good question. I don't have any prepared benchmarks for that piece exactly. More generally, I would say that I think it would probably be similar to the vec clear step, because if you imagine it's just the ability to not do an allocation when previously there would have been an allocation. So, if you're doing that in a tight loop, it is gonna make a difference. It is, those nanoseconds are gonna add up. If you're doing this function, one time, or it's a infrequently called thing, you're probably not going to see a significant performance benefit from using cow, or really any performance benefit if it's not part of a tight loop.
Cow also has a branching overhead, right?
That's correct. Yeah, it does have a branching overhead. So I think generally branching is going to be less expensive than allocation, unless you're doing very cheap allocations. But
or always allocating.
Sorry, what was that?
Or if you're always allocating.
Yeah, or if you're always allocating. Yeah, I would need to do some benchmarking to nail down when exactly those two things evened out. But generally speaking, if you have something in a tight loop that can be, if you have like a string allocation or a vec allocation in a tight loop that could be replaced with a cow, you're probably going to see benefits from that. All right, moving on to the last memory reuse topic, are arenas. So an arena is basically a pool of pre-allocated objects sitting around in memory. So instead of allocating, say, a new string or a new vec when you need one, you just grab it from the pool, and then instead of doing a deallocation, you just return it to the pool. So for my purposes, I had to create my own because I had some specialty needs around my arena, but it's a very simple type to create in Rust. The reason that I needed to create this special case type, I will allude to in the multiprocessing section, but suffice to say, I needed to read lines from my IO object, and then at some point later in time, I needed to process an unspecified number of them. So I created these two pools, the live pool, which held valid strings that were read from the IO object, and then I had a dead pool, which contained strings after they had been processed and could be reused for saving on an allocation. So my pool basically had two methods on it: take live, which pulled a string out of the live pool, and then that data would be processed and made invalid. And then the drop handler, take live actually returned like a wrapper struct around the string, and when the drop handler on that wrapper struct was called, the string was returned into the dead pool automatically, so you didn't have to remember to do that. And then similarly, the dead pool has the pool has a method on it called takeDead, which pulls a string from the dead pool with a wrapper struct around it. You can then write data into that string, and when the destructor is called on that wrapper struct, the data will be returned into that live pool. So yeah, again, arenas just allow you to save on some allocations. Next, moving on to parallelism. So similarly to the maxim that I had earlier, if you can't solve a problem slowly, you probably can't solve it quickly. If you cannot solve your problem with one core, you probably can't solve it with many cores. So the first step is to identify, what your algorithm is with one core before you can start moving on to parallelizing it. So very, very simply, the algorithm that I was following was, read a line from our IO object. If you did read a valid line, then process it and then try to read another one. But if you hit the end of file, then move on to collecting all the results and presenting them to the user. So this is the single-threaded version. And if we were to draft a sort of naive multi-threaded version, we might end up with something that looks like this. We have one IO thread that sits out there basically running the single-threaded algorithm, and multiple worker threads that do all of the processing, because this is the processing that these guys do is very parallelizable. It's totally independent between the various processors, and we can do a pretty simple merge step at the end to get all of the data to come back together. So this is sort of the naive algorithm, but in practice, it does run into some problems. Okay, I have to refresh this because I have to be able to show my throughput graph. It's too... I can't just not show my throughput graph. Okay, here we go. Now we can see it. Beautiful. Okay, so this is my throughput graph, and yeah, I didn't get to show it earlier. So as you can see, the Python version, it doesn't even show up because it's at 0.5 megabytes per second, so it's very hard to see on here. We can see the initial Rust rewrite that has none of these performance things in it was significantly faster, but when we unlocked the parallel performance, we started to get some significant gains. However, the initial parallel version that I wrote is not the beautiful V6 bar on here. It is actually the V4 version. And eagle-eyed viewers may notice something about the V4 version. It's actually slower than the version that preceded it. So despite going from 1 core to 16 cores, you know, totally maxing out, and I think at one point I even rented a 32 or a 64 core machine on some cloud provider to see what it looked like. Performance actually got worse in practice, and I noticed that like 90% of the time was spent in I/O waiting state with this version, and I did some analysis, some profiling, and I determined that this distribution step right here, the problem of taking the lines and sending them out to the various worker threads, that was the major bottleneck. And for this problem, I was using the Crossbeam channel crate, which the Crossbeam family of crates are really fantastic. I'm not trying to, you know, slag off the Crossbeam folks. They work great. They are the core of a lot of Rust async ecosystem. They fill their purpose very well, but for my purpose, I discovered that they were not doing the job that I needed them to. So that's fine. They fill other people's needs very well, but they didn't meet my needs for this problem. And again, being able to measure the performance was super important here, because I absolutely believed that this initial parallel version was going to be, you know, 10, 15 times faster than the single-threaded version, and it was actually 20% slower. So being able to measure was super important there. But yeah, I decided to maybe simplify how I was doing the I/O work a little bit. So the I/O still couldn't be totally distributed. I mean, fundamentally, we have an I/O object, which if you want to read from it, you have to take a mutable reference on, which, you know, fundamentally constrains you to being single-threaded. But what if instead of having one I/O thread that requires us to then distribute lines to all the various worker threads, what if the I/O thread was floating? And we could accomplish this by using a mutex, which would, you know, just allow us to distribute the reads onto the various worker threads directly, and, you know, have them do their own I/O when it was necessary. So I just wrapped the I/O object in a mutex, wrapped that in an arc, and distributed that arc across to the various worker threads. And I also used the parking lot crate instead of the standard libraries mutex. I found that this performed better on most operating systems. Parking lot is a crate that has locking primitives that are basically better in most ways than the standard libraries primitives. And the standard library types can't be updated because of, you know, stability, API reasons. So for folks who like care about performance or some of the other features of parking lot, you can opt into the crate to get those features. But I opted into it and saw much better performance here. So given this new structure where we're going to distribute reads onto all the various worker threads directly, we imagine that this is what our work is going to look like in a perfect world. So there's going to be a little bit of blocking that takes place at the beginning so that the various threads can wait for that mutex to become available, but then we're going to have perfection after that because of the perfect little offsets from the previous blocking. Like the IO locks are just going to line up with each other, and we can see like there's never really a time that's necessary for us to do blocking again, because the computes are going to take the same amount of time, the IO is going to take the same amount of time, and it's just going to be perfect. We're going to have a little bit of blocking in the beginning, and then we're going to move on. Done with blocking. Thank you. No thank you. This does not really pan out in reality, however, unfortunately, because in reality, sometimes compute takes longer, sometimes IO takes longer, sometimes it's faster on certain threads or less fast. So in reality, there's always going to be some amount of blocking that sneaks its way into there. And I wanted to be able to eliminate this blocking because, again, I was treating this as kind of an academic exercise, not something that I needed to maintain the code on forever. I just wanted to see what the performance possibilities were here. And so I thought, instead of having only one opportunity for each thread to take the mutex, where it would have to block if it failed that opportunity, what if each thread actually had multiple opportunities to take the mutex, and if it couldn't take the mutex because some other thread had it, what if it could just keep going, keep doing compute? So what I did instead is I divided each compute block into multiple subsections. So basically I read in a big chunk of lines from the IO object at once, and instead of processing all those lines in one go, I broke it up into multiple subsections, and at the boundary of each of these subsections, I would check to see if the mutex was locked, and if it was, I would just keep going, like totally fine, no problem, keep going, there's more lines to process. However, if it wasn't locked, if no other thread was using the mutex, grab it optimistically and refill your buffer in memory. So this basically just gives us more opportunities to try and lock the mutex, and it gives us opportunities to keep running if the mutex was not available. So this basically just gives us more chances to roll the dice and see if the locks can perfectly line up so that blocking is not necessary. So this isn't going to work for every single workload. It works when your compute takes a lot longer than your IO, but if that variant is sort of not upheld, then you're probably not going to see benefits from this, and you might actually see detriments. Well, if your compute takes a lot less time than your IO, then you're probably not going to see significant benefits from doing multiprocessing anyways, or parallelism anyways. Yeah, but I saw, again, you know, a minor but meaningful performance bump when I added this in. So let's take a look at what some code for this change maybe looked like. So this is the initial version, the sort of naive version. We have our IO object wrapped in a mutex. We have some code that reads in a batch of lines from the IO object at a time. We get the lock on the mutex. We read in batch size number of lines from the IO object. We drop the lock, and then we do our heavy computation. So this is that initial version where we were just sort of hoping and praying that the mutex locking lined up, but in practice that didn't really work, and we did actually get into cases where we would get blocked, you know, right here. And then we have to sort of refactor this a little bit. We have to take that IO interaction, we have to extract it into its own function because we're going to call it more than once. So this is the same algorithm, just broken out with a helper function where the IO interaction, the buffer filling, is part of this helper function called fill. And then we do the extra step, the mutex stealing, so I was calling it step, where we try optimistically to take the lock, and if we can take it, we do the fill operation. If we can't take it, we just keep on trucking. And we can see here, we're now calling do heavy compute with the drain iterator from earlier, and we're giving it a limit of either all of the items in our lines buffer, or a quarter of the lines in our buffer, just sort of according to how many things are in there currently. So this allows us to, again, keep going if there is capacity to keep going, but if the IO lock is available, we'll take it, we'll do our IO, and then we'll keep chugging along. So in practice, this significantly reduced the amount of blocking that was necessary on the IO lock. Questions on this one or anything else in this parallelism section so far?
How do you measure the amount of blocking on the lock?
I did measure the amount of blocking, and I did see a meaningful reduction. I did not save those numbers, unfortunately. I would need to recompute them, but I think in practice, I think in practice that difference was this difference right here. So you can see it is like a meaningful difference to throughput between these different versions when this Mutex stealing was added.
But you just timed sort of the entire process. You don't have you didn't sort of get any overview of how much time was actually spent blocked compared to doing compute.
Yeah, so when I was initially doing this optimization, I did actually put specific timers around the blocking and the compute to see how much, what percentage of time was spent in the mutex locking and what percentage of time was spent doing compute. And I did see that making this change led to a reduction in that blocking time. I didn't save those numbers.
And you had to time it manually. There is no easy tool to figure it out.
Unfortunately, there's not an easy tool to figure it out, but in practice, it's relatively easy to add, time instant now before the mutex lock call, and then duration, or what is it called? Since, I think, or elapsed on that instant that you get to see how long it took, and then just sum those up as you go along. Yes.
Sorry, maybe I missed it. But you were saying that little gap between version 6 and 7, that was the sealing the I/O. What is the major thing between version 5 and version 6?
That's a great question. Version 5 and version 6 is going from the naive multi-threaded version where there's channels shooting things around to the IO mutex version.
Cool.
Where each worker thread does its own IO. So that is what just sort of unlocked everything and allowed it to really be parallel and to not waste its time doing in-memory blocking operations. Alrighty. So summarizing once again, we improve performance on the single core by reusing memory. So instead of allocating a new vector, we can just clear out an existing vector. Instead of iterating over a vector with into iter, we can use drain, and that allows us to reuse it. Instead of returning strings and allocating where unnecessary, we can use a cow. We can use memtake to pull items out of a mutable reference, which could be used for scratch storage on a struct. Transmute allows us to change lifetimes in very limited circumstances, and arenas allow us to have a pool of objects in memory and save on allocations from those objects. With parallelism, it's super important to make sure that you are actually parallelizing your compute and not just spending all your time in a IO blocking state. Choosing which mutex you want to use can also help give you a slight performance boost, and sometimes optimistic mutex lock stealing can allow you to get an additional 10-20% performance on top of your parallel code. So that was all the content and strategies I had prepared. Thank you so much for giving me the opportunity to talk to everybody today. Check out my book, Refactoring to Rust. I am currently writing a chapter on making Python code faster by using the Pyo3 library to write extension modules with Rust. And that chapter actually includes a section on how to use the criterion tool to benchmark both Rust code and Python code to validate that your Rust version is actually performing within the constraints you expect. So I hope you check that out. And I know that Eric shared a code for a discount. You can also use the code MLMERA for 50% off at manning.com. So check out my book. Follow me on Twitter, @Lily_Mera. Check me out on GitHub, Lily-Mera. And yeah, thank you so much, everybody. Any final questions from anyone? All right. Well, I really enjoyed getting the chance to speak with you today. Thank you so much.
Yeah. Thank you very, very much.
Yeah.
Yeah, I don't know if we have any, like, we'll give a few seconds in case someone thinks of a last minute question.
General Rust questions. It doesn't have to be about optimizing specifically. I've been using the language for a long time and seeing a lot of stuff change. Yeah, something in the back?
Yeah, did you use the system allocator, or did you try to use JA-malloc?
That's a great question. I did not try using JMalloc at any point, but that's something that I suppose I could try to swap out, because that is thankfully at this point relatively easy for us to swap out.
I actually have one question. I
Okay.
just thought about you didn't go that much into like the string arena thing.
Okay.
But it's that like I've thought several times about like trying to get the same thing as like the Java string pool, where you have like you read a lot of random strings, and then but you only want one instance of each string in memory. You want to throw away all the rest.
Right.
But I haven't dove deep enough into it to like figure out like how do you do that to actually have it be performant and actually being allowed to share that memory across your application.
Yeah.
Because like it seems like it would do the transfer memory across that you then figured out wasn't that performance.
Right. So the thing that like allowed this to work is that this step right here, where I actually, used the data in the strings, this took a string reference, like a string slice. It always did that. I tried to make it operate on slices wherever possible. And so that meant that the function that like was using the arena never had to give up ownership of the string to anywhere else. So I could actually, I suppose, pull up the code if folks are interested in sticking around and doing code spelunking.
Yeah.
So that's in the parallel cluster, because the single threaded version actually doesn't need to have an arena at all because its algorithm is so simple. Wait, where is it? Okay. So this is the code that pulls items. So is this readable, or do I need to make this bigger? I can make it bigger if necessary.
It's slightly bigger. The resolution isn't super high on the transmit for some reason.
Better?
Great.
Okay. Yeah, so this is the code that pulls the items out of the pool. So you can see I use take live to take a string that was previously read in from the IO object. And then I pass it to this cluster.processLine method, and I use asRef here to pass in a reference. So this line, it's only this line, this own thing, it only exists for this teeny tiny little scope right here. So as soon as we iterate again, that line is dropped and it's returned back to the dead pool immediately, because it shouldn't be processed again. So the fact that this thing takes a reference means that I don't have to worry about like a move in validating the memory because of like I don't have to worry that this thing takes an own string, and so it's going to call the drop handler for this other thing. I don't have to worry about you know, getting that memory returned to me by process line, if that makes sense. Okay.
Interesting. I'll have to thanks.
Any further questions?
I have a question.
Yeah.
You said you had the process struct that had like a swap space.
Mm-hmm.
You wanted to keep a vector of cow of static slices.
Yeah.
But you transmuted like lifetimes into static lifetimes. Doesn't that mean when you drop the process struct that they aren't deallocated because static references aren't deallocated? So it creates a memory link. But I guess that's okay.
No, that's not going to be the case, because so this is the actual, well, I think there's actually, yeah, this is the actual thing that I'm doing that transmute on in practice. And I believe in practice, between every iteration of process line, what is this thing called? Pattern backing storage. Yeah, so between every iteration of, or between every call to process line, it is either replaced with a valid value, or it is cleared. So like the key like innovation and safe thing about that function, that clear and reinterpret function, is the very first thing it does is clear out the vector. So everything that was previously in there is deallocated, you know, at that time. The only thing that's not deallocated is the buffer space itself. So there's not going to be a memory leak because that clear is in there. Like if that clear was not in there, then the whole function would be like it would almost certainly have undefined behavior in it. But also it is important to note that from the perspective of the Rust compiler, you know, a memory leak is safe. You know, you can totally leak memory in 100% safe Rust, and you sometimes do have to, actually, in order to use certain APIs that require like static strings. Yeah, it's sometimes necessary, and it sometimes happens without necessarily thinking about it, but I don't think it happens in this case. If there's nothing else, I think I will leave you. So thank you so much, Rust Oslo. It was really great talking with you today, and I hope everybody has a great rest of your evening. Bye.
Bye.
Right.